move to next example. So this is a, you can see that this is a second degree of 2-degree of freedom system. This 2-degree of freedom system is consisting of two massless rods. At the ends of each rod, there are two masses, M1 and M2. First rod is hinged at the ground, and at each joint, there are some external torque applied, tau 1 and tau 2. We will follow the same procedure to get the equation of motion. Now again, this is a 2-degree of freedom system. So how many equations will have? We'll have 2 equations of motion. What are the coordinates? Here generalized coordinates are theta 1 and theta 2. Now we have to find out what is the kinetic energy of the system and what is the potential energy of the system to define the Lagrangian of the system. So in the first line I have written kinetic energy of the system. So kinetic energy has two parts: kinetic energy related to mass 1, kinetic energy related to mass 2. What is the velocity of mass 1? We know that the velocity of mass 1 is L1 theta 1 dot. This we have done in our previous example. But what is the velocity of mass 2? This is not straightforward. The velocity of mass 2 can be found out. It is the velocity of mass 1 and the velocity of mass 2 with respect to mass 1. That is the total velocity of mass 2. There is another way to find out this velocity. The way is, let us assume the position of mass 2 is given by x2, y2. Just beside the figure, I have written position of mass 2 is x2, y2. And this x2 and y2 are defined just below it. So x2 is given by L1 is the length of the first rod, cos theta 1, plus L2 cos theta 2. That is x2. And then y2, just below it, we have defined y2. Y2 is equal to, similarly, we get L1 sin theta 1 plus L2 sin theta 2. So that is the position x2, y2 given by this theta 1 and theta 2. And let us, so once we have x2 and x1, these positions, what is the velocity of velocity v2 of mass 2? v2 of mass 2 will be given by x2 dot square. The velocity square will be equals to x2 dot square plus y2 dot square. Because why it is so? Because see, the vector component of velocity of n2 in the x direction is x2 dot, in the y direction is y2 dot. So, and these two quantities are perpendicular to each other. So the absolute velocity will be just square root of these two velocities, summation of these two velocities square. So that means v2 square can be given by x2 dot square plus y2 dot square. So we have calculated this x2 dot and y2 dot beside the definition of x2 and y2. Just take derivative with respect to time and you get x2 dot and y2 dot. One can check. Let us consider this x2 dot. x2 is given by L1 cos theta 1 plus L2 cos theta 2. So if you take time derivative, so this is minus cos theta derivative minus sin theta 1 and theta 1 derivative with respect to time theta 1 dot, and similarly the next part. So once we have calculated this x2 dot and similarly y2 dot, substitute this x2 dot and y2 dot in this v2 square relationship. So once you substitute it, you'll have and with some simplification, we will have the expression for V2 square. Once we have V2 square, you substitute it in the top expression for kinetic energy T. Now we know what is V2. So by substituting this quantity expression of T, we get the definition of kinetic energy. Okay, so this is the kinetic energy given by half m1 l1 square theta 1 dot square and so on. This is just substitution of this v2 square in the expression of T. Once we have kinetic energy, now let us find out what is the potential energy of the system. Again, the potential energy of the system is the gravitational potential energy. Potential energy related to the first mass is m1 gl1 sin theta 1, because the vertical distance from the horizontal x-axis for mass 1 is l1 sin theta 1. For mass 2 it is l1 sin theta 1 plus l2 sin theta 2. Remember one thing, that we have taken this positive x-axis as V0 level. That means the gravitational potential energy dot term is this positive x-axis. One can choose this dot term anywhere, any horizontal line you can choose at V equals 0, and you can calculate the potential energy of the system. But for simplicity, we have chosen this V equals to 0 is the positive x-axis. So from that, the mass 1, distance of the height of mass 1 and height of mass 2 we have calculated, and we have defined the potential energy of the system. Just bottom of the slide we have mentioned this potential energy. Then some simplification, we have the simplified form of this potential energy. In the next slide, we will define the Lagrangian of the system. The Lagrangian of the system will be T minus V. Okay, so before we define the Lagrangian, we have written the Lagrange equation of motion. As we have already mentioned that there are two equations of motion because the degree of freedom is 2. First equation is associated with the derivatives of with respect to theta 1 and theta 1 dot, and the second equation is associated with derivatives with respect to theta 2 and theta 2 dot. So now we have here shown the Lagrangian L. L is defined as T, expression of T minus, in blue colors we have given the potential energy. Okay, in blue colors we have mentioned the potential energy, which we have already found in our last slide. Now again, what we will do, we have to substitute these derivatives. We must determine these derivatives. First step is to take derivative with respect to theta 1 dot. So the derivative is given here, and then we have taken the time derivative of this quantity, which is to be substituted in the first equation. The first term is now calculated. Next term is del L del theta 1. So we calculate this derivative. That means derivative of Lagrangian with respect to generalized coordinate theta 1. So once we have calculated this, the first equation, two terms we have calculated. Now we have to calculate the generalized force Q1, and for second equation all the quantities we have calculated. That we will do in the next slide. So again, I have for your reference, I have again written the same Lagrangian, and then now for this second equation, second Lagrange's equation, which we have mentioned here in this slide. Second equation. For second equation, we now will calculate the derivative with respect to theta 2 and theta 2 dot. So we calculate this derivative theta 2 dot, and then you take the time derivative, so you have this expression. And the next term is derivative of Lagrangian with respect to theta 2, that has been calculated here. Next step is to write the virtual work related to this external forces. The virtual work related to this external forces is virtual angular displacement theta 1 multiplied with the torque tau 1 plus virtual displacement of second rod angular displacement. Virtual angular displacement is delta theta 2 multiplied with the torque, external applied torque tau 2. That is the virtual work related to externally applied torque. Now we have the expression for Q1 and Q2. So again, we call it generalized force, but it can be a moment. So then we have substituted all the quantities in previously mentioned two Lagrange's equation of motion. First was associated with theta 1 and second is associated with theta 2. So now we have these two equations, this equation 1 and equation 2. These two equations gives you the dynamics of the system. These are the governing equations of the system. Solving these equations, you will get the dynamic behavior of the system. Now, the solution of the system, solution of this equation is not part of our this talk. So we will be developing only governing equations or equations of motion of the system. So these are the two equations of motion for the system. The system we have here discussed is the 2-degree of freedom system. In this 2-degree of freedom system, we have massless rods and point mass. What is the advantage of considering these point masses? The point masses only have a translational kinetic energy. It will not, they don't have because the mass is concentrated here and it has no rotation, there is no rotational kinetic energy. Now we will consider a situation where the mass is distributed, and we will find out what is the equation of motion using Lagrange's equation of motion. This is again is a 1-degree of freedom system. In this 1-degree of freedom system, look at the figure. So there is a rod where the mass is distributed. The moment of inertia of this rod is, say, I1 with respect to one axis passing through its center of mass, and the axis is perpendicular to the plane of motion. The mass of this rod is total mass is, say, M1. The configuration at any time, configuration of this rod is completely defined by this coordinate theta 1, because we need only one coordinate to completely define the position of this rod. Why? Because at any instant this rod is rotating with respect to this hinge point. Suppose at any instant it is rotated by theta 1 angle. So to find out any point on this rod, you need to just know what is the distance from this hinge point you want. So you can define any position on this rod at any instant with this one coordinate theta 1. The degree of freedom of this 1. So equation of motion, just below this figure I have written Lagrange's equation of motion. There will be only one equation of motion, and the derivatives of Lagrangian will be with respect to theta 1 and theta 1 dot. So first task is to define kinetic energy and potential energy and define Lagrangian, and then you take derivative of this Lagrangian with respect to theta 1 and theta 1 dot, and replace it in this Lagrange's equation of motion. So what is the kinetic energy of this system? Now here you see one thing, that the system is a distributed mass system. So it will have this kinetic energy will have two parts. I have written here T equals to TTR, that is associated with translation of kinetic energy, and the kinetic energy T rho means rotational kinetic energy. Translation of kinetic energy and rotational. Translational kinetic energy will take what is the velocity of the center of mass of this rod. Velocity of the center of mass of this rod is nothing but L by 2 theta 1 dot. What is the velocity at the top of the rod? It is L theta 1 dot. But we want velocity of the center of mass. So velocity of center of mass is half L theta 1 dot. So first part of kinetic energy is, now this is half m1, and this velocity is square, that is L1 theta 1 dot square, plus what is the kinetic energy related to its rotation. Kinetic energy related to its rotation written half I1 is the moment of mass moment of inertia of this rod with respect to one axis passing through its center of mass, and theta 1 dot square. This is the kinetic energy, rotational kinetic energy. So this rotational kinetic energy now calculated. That is this is a rod, and this rod, the moment of inertia is given by this 1 by 12 ml square. Mass is m1, length is L. So 1 by 12 ml square is the moment of inertia. We have substituted it here. So finally, with some simplification, second line we have the definition of this kinetic energy of the system is 1 by 6 m1 L square theta 1 dot square. Now what is the potential energy of the system? The potential energy, now since this mass is distributed, we consider, and mass is evenly distributed, so we consider the mass is concentrated for potential energy. Although one can do an integration and find out what is the potential energy, it will be the same thing. The mass, we have calculated the potential energy with respect to the center of mass. So that is half, that is 1 by, this is 1, right? There is another typo here in the expression of E. This is half m1 gl sin theta. Okay, so actually mg L by 2 sin theta. m1 g L by 2 sin theta 1 is the potential energy of the system. Now we define the Lagrangian. L equals to T minus V, kinetic energy minus potential energy. Then you calculate the derivatives. First calculate derivative with respect to derivative of L with respect to theta 1 dot. This is 131 L square theta 1 dot. Then take the time derivative of it, that is 131 L square theta 1 double dot. The second quantity is del L del theta 1, derivative with respect to theta 1, that is half minus half mg cos theta 1. And the virtual work associated with is defined below. This is tau 1 is the externally applied torque, and the virtual displacement, angular displacement is delta theta 1. So this is the virtual work, tau 1 delta theta 1. From this expression we get the generalized force substitute all these quantities in the Lagrange equation of motion. So if you substitute all these quantities in the Lagrange equation of motion, we get final equation of motion, which is written below. Just the bottom of the slide I have mentioned here. This is the equation of motion of this rod. Okay, let us move to the next example. First, let me describe the system. The system is a 2 degree of freedom manipulator. Here there are 2 rods. First rod is hinged at the ground, and then the end of that rod is connected to another rod by a hinge joint. There are 2 joints. At each joint there is a external application of torque tau 1 and tau 2. Since these are 2 rigid bodies connected with each other, the degree of freedom of this system is 2. How the degree of freedom of the system is 2? For the first mass, for the first term, we know already, we have discussed the degree of freedom is 1. In the second, suppose there is a rod which can move in one plane. Our discussion is restricted to planar motion. So suppose the rod can move in one plane. That means what is the degree of freedom of that rod? If it is free in one plane, it has 3 degree of freedom. 1 degree is its rotation about one axis perpendicular to that plane, and 2 other are 2 translations. Now, when we hinge that rod at some point on the plane, what happens? We restrict its translations. That hinge point restricts its translation in any direction. It cannot translate, because with respect to that hinge point, the hinge point is fixed, so it cannot translate. Only it can rotate with respect to that hinge point. So we have at least 2 degrees of freedom. Now what is left? 1 degree of freedom. So the system here has 2 degrees of freedom, and the generalized coordinates are here theta 1 and theta 2. One thing to notice here is the coordinate, choice of coordinate. We have chosen theta 1 with respect to positive x-axis, that is the orientation of this rod. Also, we have chosen theta 2 with respect to positive x direction. One can choose another direction also. One can have a axis along the first rod. Along the length of the first rod, one can have one axis. With respect to that axis, you can choose your theta 1, the orientation of the second rod. Okay, so just equations of motion, the expressions will little bit change, but the dynamics will not change. Then again, you can always express that the other angle that you have chosen. If you choose, the dynamics will be the same. The equations of motion will slightly change. That is just coordinate transformation. One coordinate system, another coordinate system. What I am trying to say that you can choose your own way of selecting coordinates. So here we have chosen this system. This theta 1 with respect to positive x1 direction, theta 2 with respect to positive x1 direction. Okay, so degree of freedom of this system is 2, and the length of first rod is L1, length of second rod is L2, mass is M1, and the first rod, mass of the second rod is M2. Moment of inertia are I1 and I2, gravity acting downward. So here our first step is to define the kinetic energy and potential energy of the system, which are required to define Lagrangian of the system. So let us define the kinetic energy of the system. I have written here T equals to T1 plus T2. T1 in blue color is the kinetic energy associated with first term, and T2 is associated with second term. So first, blue colors, again I have written T1 equals to half A1 dC1 square. C1 is the center of mass of first term, and C2 is the position of center of mass of second term. So here we have, for both terms, we have translational kinetic energy and rotational kinetic energy, which we have written here. So first of all, the first part of the kinetic energy already we have discussed in our last example, that is given in blue color, that is T1 equals to 1 by 61 L1 square theta dot square. That is the kinetic energy of the first term. But what is the kinetic energy of the second term? So you see here, only unknown we need to determine is the velocity of center of mass of second term. How to determine that? Here is one method I am following. Let us assume that the center of mass of second mass is at xc2 yc2, because the point is mentioned here by the name c2, so I am writing xc2 yc2. How is xc2 and yc2 is defined? So along x direction, xc2 is given by L1 cos theta 1 plus half or L by 2 cos theta 2. Okay, similarly, we can define yc2 is L1 sin theta 1 plus L by 2 sin theta 2. Okay, so this way we have now defined the position of center of mass of second arm. Then we have to find out what is the velocity, again from our previous discussion. The two derivative of these two coordinates xc2 and yc2 will give us velocity of the center of mass of second arm along x direction, along y direction. Since these two velocities are perpendicular to each other, then we can find out its absolute velocity by just squaring, adding, and then taking square root of it. So that is why the velocity square of the center of mass of second arm c2 square is given by xc2 square or c2 square. And now substituting these derivatives, already we have calculated here. Substituting these derivatives, we have now expression for vc2 square. This vc2 square, we will substitute this into the expression of kinetic energy. Finally, we have the kinetic energy T equals to, the first part is 1 by 6 m1 L1 square theta 1 dot square plus the second part, where half m2 into bc2 square, which we have calculated here. And now what is the potential energy of the system? The potential energy of the system, again, for the potential energy of the first arm, which we have calculated in our previous example, and then we have to write down the potential energy associated with the second arm. Again, we want to mention here that this positive, the ground level is the zero potential energy level. So here we can define, now the potential energy is defined. So in the next slide, we will define the Lagrangian of the system. So here I have written down the equations of motion. Again, we have 2 degree of freedom system, so we have two equations of motion. Lagrangian is defined here. Once you have this Lagrangian, just T minus B, kinetic energy minus potential energy. The blue color I have written here is the potential energy part, and then you need to calculate. The process is the same. You again do the derivatives with respect to theta 1 dot and theta derivative of the Lagrangian. So I'm not describing all these terms. They are just calculations of derivatives. So you get the derivative, and so derivative with respect to theta 1, theta 1 and theta 1 dot, and derivative with respect to theta 2 dot and theta 2. So all the derivatives are done. Then the bottom is this slide. You can see we have calculated, we have determined the uh, potential virtual work related to this externally applied torque C1 and tau 1 and tau 2. Once we have all these quantities, then we will substitute all these quantities into this Lagrange's equation, which we have mentioned in the top. In these Lagrange's equations, we will substitute all these quantities, and then we will have equations of motion of the system. Okay, so this is the equation of motion of the system. There are two equations. First equation is related to theta 1, and second is related to theta 2. Although these equations are highly nonlinear equations, they are interconnected, so they will determine the dynamics of the system. So you can imagine how complicated the dynamics is, but this is very necessary because you want a particular kind of motion of your manipulator, but what is the torque required, how it should mm, how it should be, and for a very long kinematic chain, uh, you have to find out dynamics of the arms. Okay, so this way you can find out, you can write down. The first step is to write down the kinetic energy of the system, the potential energy of the system, define the Lagrangian of the system, then calculate all the derivatives. Once you have calculated the derivatives, if there is some torque acting at the joints or force acting related to the torque or force, you calculate the generalized force and substitute all this into the equations, and you get the equations of motion. Okay, so with this, I want to finish this session, and I will be pleased to answer your questions.
Good morning, sir. Jitendra Prajapati is here.
Okay, please.
Hello. Yes, sir.
I can hear
sir,
you.
in two-link real manipulator, we are finding the actuator and different sensors are also on the link of the manipulator. So, if we are not considering that and apply this model, is it possible to find the dynamics of two-link manipulator?
See the sensor, the sensors. There are two things you said. One is sensor, one is actuator. Okay. So first question is associated with sensor. Sensor is just like a mass. Okay. So in the rod, in the manipulator, this is a mass. So you consider the mass. If you have the sensor's mass is uh, very high compared to the manipulator mass, then the moment of inertia of that rod will change. But if the sensor's mass is small compared to the mass of the manipulator, then we need not to consider that. It is a negligible thing. The next part of your question is actuator. Actuator is actually moving part. Okay, if there is some actuator, that actuator, it may be a prismatic actuator, it may have some revolute pairs, there will be moving parts, we need to take care of these also. Okay, so they will add to some other degrees freedom system, you need to take care degree of freedom of that actuator also.
So it should not be
Okay.
directly added to the mass of the link. It should be considered a separate mass.
You need to take care. See, if there is a prismatic pair, okay, if there is a prismatic actuator, or if there, then what is happening there? So there is one mass and another mass is sliding through it. So it is having another degree of freedom. Okay. So then the same way, this is the same. I have taken two revolute joints. Okay. So you have to add another prismatic joint with it. Right.
Correct. Yeah.
Okay.
Okay. Thank you, sir.
Any other question, please? There is a question. Please share the content. We will share the PPT. Okay. Any other question? See, again, I want to say that this is very important topic. Although uh, if you are really going for a complicated motion, there you need to take care of dynamics of the system. So the dynamics of the system and this Lagrangian mechanics is very helpful to get the equations of motion. Now with the advancement of computers and computing facilities, we are able to solve these equations. There are computing in MATLAB, you can solve these equations, and I don't know about other softwares, but using MATLAB, and before that you have to uh, simplify these equations. Okay. There's a question: if there is a spherical joint, how is the modeling? If there is a spherical joint, the we are not here. What we need to consider, if there is a spherical joint, that means the motion is not constrained to one plane. Now it's a space motion. So how many coordinates you need to specify the the manipulator which is joined through a spherical joint? Okay, how many coordinates do you need? So that degree of freedom you have to add, and for each degree of freedom you will have some kinetic energy associated with it. All those coordinates you have to take care. Just write down the kinetic energy and potential energy of the system which involve these coordinates. So once you can write down this kinetic energy and potential energy, the formulation is same. There is no difference. The difficulty, the same thing, the spherical joint thing, same thing when you do in Newtonian mechanics, there is huge difficulty. But when you do it in Lagrangian mechanics, so it is easy, because you have to just write the kinetic energy. You need to take care what are the degree of freedom of the system, how many coordinates you need to specify, completely specify its position if there is spherical joint. So you give one practical session on any software. So you see this, we can show you this how to solve these equations. Okay, but to write down the equations of motion, that you have to do it by your own. Yes, I think dynamic modeling can be done in softwares. I think, if I'm not wrong, Adams is there, although I have not used that software. See, what I have tried here, I have tried to keep our discussion simple so that you can start from very basic and do your own analysis, so that you can have faith on your own. You can write down your equations and you can solve. And these slides, if you follow, these are very. I kept it very so that it will explain everything. And my suggestion will be, you solve the same problems, the same problems which we have solved, the 6 problems we have solved one by one. You solve the same problems by your own, practice it, have some confidence, and then you will be able to write down equations of motion for any kind of system. So, but see how to find dynamics of 5 and 6 degrees of freedom. See, a question is there, how to find the dynamic of a 5 or 6 degree of freedom system. The same, the method is same, the same way you can find out. And now, after doing this, now if you follow a book on dynamics, there is a formal way. They do this in matrix form, they will write this in matrix form. The basis is this. First, you have to learn this. Once you learn this, once you have confidence on this, then the next is very simple. Once you have confidence on this, the next you can follow any book and you can write down the equation of motion for 5 degree, 6 degree, n degree of the system. You can write down equations, but you have to take help of computers then, because at that time this and calculations will no more work. Sir, can you please give me idea how to study dynamics and kinematics of wheel mobile robot? See, I have not expertise in wheel mobile robot. I have done work on dynamics and vibration is my field. I work on that, and it is not different. You see, this is the basic idea. You have a problem. You can just model it. You can model it, and then you write down the equations of motion. You have a joint. Once you have a joint, you know what is the degree of freedom allowed. Then you have defined what is the required coordinate system. Okay, once you have defined that, write down the kinetic energy, potential energy, everything is done. What are the basic mathematics for robot dynamics? See, I am talking about only this Lagrangian formulation. So with respect to that, I can say that uh, you can follow a book if you are interested in the proof of this Lagrange equation. There is a proof. Obviously, you can go through that so that you will have understanding how this equation come into existence, and what are the limitations. Means you cannot blindly apply everything there. If some complicated situation is there related to non-potential forces, then you have to read and practice. Dynamics is dynamics. It's same in everywhere. So okay, I'll refer to that book also. Or you can analytical mechanics. You can go study DT Greenwood. for analytical mechanics. There is a book by Goldstein. It's a very famous book. You can always find out on for analytical mechanics. But I will suggest again and again, I will suggest the problems which we have solved here. You go and solve the same problems by your own to have some confidence on it. I really do not have any idea about redundant robot, and if you personally contact me, then I will obviously go through this and see what can be done. So the concepts are same. Concepts, the basic is this. Okay, you give me any problem, you have to approach through it, and if you have good understanding of the subject, you can solve any problem. Any other question? If there is no other